Hello students, it is lecture number 16. Okay, and we are into chapter number 4. Okay. So the story so far is there is a boundary value problem. Okay, and we want to solve it. Since exact solution may be difficult to obtain a lot of times, so you want to have the approximate solution. Okay, so there are various ways of solving or obtaining the approximate solution. One of the thing is known as Galatian method, in which you need to have a weak formulation, right. So, a weak form you need, okay, of a strong form, that is differential equation. Equation plus boundary condition. Okay. Okay. So, we will be using Galatian method to solve it, and Galatian method has two things you have to know. One is the test function, we call it ux, and then there is a weight function, we call it wx. Okay. So, in the last lecture we actually looked at the test function, which is ux as a piecewise polynomial, and this is the what makes it a finite element analysis. Which one? The piecewise polynomial. Okay. So, piecewise polynomial is a characteristic of finite element method. Okay. Okay. So, we actually looked at the a piecewise polynomial, and we obtained, if this is the exact solution, and we obtained solution which was something like going from here to here and here to here when you assume the piecewise polynomial. So, this is piecewise polynomial. Yeah. Okay. So, basically now we have already have the background. The only thing remains now, things remain now. Okay. A is we want it to be more accurate. So, accuracy we have to look at. B, we have to look at the how fast it is, you know. So, accuracy is one thing, but we should also have to see the how time wise how fast it is. Okay. So, basically we have to see the time required to compute, time required, or how fast, basically or a speed. Okay. Okay. Now, we also have to see computer implementation should be something computer friendly. Okay. And if possible should be easy enough, right, easy you call it, or call it elegant. Yeah. Okay. So, this is what remains, and based on basically these things, like we are going to choose one, right. So, accuracy here, everything based on the test function, choice of the test function. So, basically our choice of the test function will depend on how much accurate we want, how fast we want, then how computer friendly it is, and how easy it is, right. So, basically look at few things, okay, some ideas. So, all those things I think I should write here, the things remain, and exactly to we choose ux and wx for. So, basically we will choose u, x and wx such that it will give accurate results, it will be fast, this will be computer friendly, and it will also be easy. So, that is what it means. Okay. So, basically we have to come up with some ideas, okay, some ideas for ux or wx. So, basically u and w, you know that they are close. So, anything whatever you are finding ux, you will take wx close to that, yeah. So, almost similar expression, however it has its own criteria to be fulfilled. For example, wherever u is given, regardless of whether it is 0 or non-zero value, u w will be has to be 0 there. So, that is the only difference, otherwise both are exactly the same. So, some ideas for ux, okay. So, which are ideas possible? So, look at that. One, it says that accuracy. So, accuracy, as we have seen here, if we had in the last lecture video, if we had like divided the whole domain into 2, then we got close to the exact solution. If you had only one, then you will get something like this, right. So, write like this, this one is, so only if only one line, then we had this solution, this is the exact solution, only one line, only one piece of polynomial line basically, then you had this solution. So, there was error here, maximum error in middle somewhere. Then if you made two lines, then this is better than one line itself, but still this is not exactly closely tracing the exact solution. So, we can even have more elements or more number of polynomials or more number of lines to fit, then it will be fitting even better, and so on. So, accuracy, we can say that increase the number of elements or increase the number of polynomials, right. So, basically solutions will be for accuracy. Let us look at one by one. So, accuracy, what you will do? Increase number of piecewise polynomial, in this case not polynomial but lines, basically lines, okay. So, this will be one of the solution, or so here I can say this is one, or increase the order of the polynomial, increase the order of the polynomial. So, what it means is, instead of line take quadratic test function. This will be one example, quadratic test function or cubic test function, etc. So, there are two ideas. Accuratic, either you have more number of lines. So, more number of lines means you will trace very closely now still linear only between 2 points, but still these lines are so small that it will almost trace the original exact solution. That is one idea. Second thing will be to increase the order of polynomial, meaning that earlier you assumed the line to be a solution, now you assume quadratic solution. Since we know that the exact solution is quadratic only, you will see that if you take only one polynomial, it is going to exactly trace the exact solution, right. So, that is another thing to do. Okay. Now, second thing is time required or a speed. Yeah. So, time required speed depends on the what? Typically in computer it requires number of the size of the stiffness matrix is the main thing, okay, because you have to invert that. Yeah. So, say B speed. Okay. So, speed we can say roughly it will translate it to the size of the stiffness matrix. Yeah. Okay. So, minimize the size of K. Yeah. So, because you have to inverting a matrix is costly, so that is why you have to keep it a minimum, and you can see in this case is if you have a quadratic one, then probably it will be easier. Yeah. So, in this particular case, right. So, meaning that if you have 10, let us say 20 of piecewise lines, 20 of piecewise lines, so your the number of nodes will be 21. So, K will be 21 by 21, and then that you have to invert. So, it will take time. Instead of that, if you have say only one the polynomial, then the size of the stiffness matrix will be a smaller. Yeah. So, maybe 3 by 3. So, why I am saying 3 by 3, we will see that, okay, later today only. Okay. So, that way this is going to reduce. Okay. So, meaning that we still have to right now, since we have not studied, if you take the quadratic test function, then how that is going to take less time. Yeah. So, but you can just see that in one case you have number of polynomial which is going to be 20, in one case you have just one only. So, even like when you are doing on using pen and paper, you know that the one which has 20 lines will be more difficult to solve, right. So, hence it will take more time. If you had just one polynomial, then it is much easier or much faster, right. So, that we can relate, but the size of stiffness matrix I will come back later. Okay. Today only, not today maybe, so maybe like next week. Yeah. But this is the ideas it is coming, and you have to check now that whether polynomial is going to give you like take less time. If it does, then choose that. Okay. Now, the C, okay, is computer friendly. Okay. So, computer friendly, meaning that, see here the what is the ideas here. Ideas like in earlier in the last video lecture we assumed ux equal to alpha naught plus alpha 1 x, right. And now, then we have to make we had two different types. This was for x which was 0 to L over 2, and then equal to probably it was beta plus beta 1 x, and that was for x greater than equal to L over 2 L. and we had to make, we have to apply so that ux is continuous at x equal to L over 2, and that means was 0 plus alpha 1 L over 2 equal to beta naught plus beta 1 L over 2, So, this condition we have to make so that is continuous. So, that means if you want to do this kind of thing on a computer, so it difficult, like why not, in that case why not have some scheme in which this automatically guaranteed that the curve will be continuous or the piecewise polynomial has to be continuous. Okay. So, that we do not have this kind of restriction, we have to check automatically, we have a scheme in which automatically it guarantees that is continuous. So, one idea would be, instead of saying constructing the test function using some arbitrary, some constant alpha naught alpha 1 or beta naught beta 1, why not use the nodal displacement itself as those constants? What I mean is, let us say you have let us say we want to solve this one, the original problem only we want to solve it. Okay. Same thing what we had B here, and we have E and A given, okay, and it is fixed here at one end, free at one end, there is no force applied here. Let us say this is the we want to solve it. Now, let us say we want to be accurate. Now, we apply everything, we want to be accurate. Okay. Accurate, so we will take n. So, let us put nodes, we will put node here. Let us say we put 4 nodes. So, 1, 2, 3, 4 nodes, right. So, we had 4 nodes. Okay. Now, if you want to construct the U, okay, so there are 4 nodes, meaning that we want to use 3 piecewise lines. Okay. So, one line here to here, another here to here, here to here. So, just to demonstrate, I am taking 3 of them. Okay. Now, we can, instead of writing ux equal to alpha naught plus alpha 1 x, I may write something like this, ux equal to, right. So, let us give the node number 1, 2, 3 and 4, and let us say the u value at 1 is u1, this is u2, this is u3, this is u4. So, we can write something like u1 equal to ux equal to u1 plus u2 minus u1 over whatever the distance between this and this, right. So, let us say the x value here, the coordinate is x1. So, let us write the coordinates. Okay. Coordinates are x1, x2, x3, x4. These are the nodal coordinates. So, accordingly we can write u1 plus u2 minus u1 divided by x2 minus x1 multiplied by x minus x1. So, what we are going to do? linearly interpolating. So, if we know u1 here, if you know u1 here, u2 here, in between it is going to vary linearly, right. So, basically between x1 and x2 we can draw like this. If this is x1, this is x2, and if this is the ux, here this is u1, here it is u2, in between it is going to vary like this. How we can write interpolation? We just interpolate u1 plus difference between u2 minus u1 divided by x2 minus x1, which will give you the length of that, right. So, we can say call it L1, length of the. So, L1 equal to x2 minus x1, basically length of the element, multiplied by x. So, if you want to find out here, so this is the x value. So, x minus x1, right. So, this way it will interpolate. You can check it. If x equal to x1, then what happens? X equal to x1, it becomes 0, hence you get u1. If x equal to x2, you have x2 here. So, x2 minus x1, x2 minus x1, so both cancels out, you have u1 plus u2 minus u1. So, u1 and minus u1 cancels out, you have u2. So, at x equal to at x2, you have u equal to u2. So, this works. Yeah. So, similarly, if you want to constitute the ux for this, automatically how you will do? You will do the similar way. So, you are going to write the this is valid for x less than x2 and greater than x1. Similarly, you can write the next one based on this only. You can write ux equal to u2 plus u3 minus u2 over x3 minus x2 multiplied by x minus x2, right. This will be equal to valid for x greater than x2 and less than x3. You can also do that, right. Exactly similar way we have writing for this one. This is for valid for node element number 2, means for the domain x less than x3 and greater than x2. So, this is what this is valid for. So, you will see if x equal to x2, then what happens? X equal to x2, you put x2 here, x2 x2 cancel, this becomes 0 and hence the whole thing becomes 0. So, you have u2. So, if you see u from both, what you see is u x2 is equal to u2 from both. Either you use this one or use this one, you automatically get u x2 equal to u2. That means continuity is maintained. Yeah. So, continuity automatically maintained. So, this is a great way to write the test function. Yeah. So, instead of writing alpha 1, alpha 1, 2, 3, 4, why not use the nodal displacement itself as a variable, yeah, and then write your u, the test function, with respect to nodal displacements only, and then this becomes easier also. We also know here that although this is a test function and this is a linear, we know everything here. We know u2. Achha, u2 means the what is the displacement at node 2. Achha, u3. Okay, what is the displacement of node 3? x3. Okay, what is the coordinate of node 3? You know, so we know everything in here and here. And similarly, you can the third line also we can write similarly. So basically, the third line will be equal to so u x will be equal to u3 plus plus we have u 3 minus u 2. So, it becomes u 4 minus u 3 divided by x 4 minus x 3 multiplied by x minus x 3. Yeah. So, this is equation valid for this one, the third element. Yeah. So, this is for x less than equal to x 4 greater than equal to x 3. So, you get the third one, and here also you can see that if you had let us check here at this point. Yeah. So, if u equal x equal to x 3, this is not valid because this is valid till x 2 only, this is valid till x 3. If you put x 3 here, then what happens? This becomes x 3 minus x 2, x 3 minus x 2. So, both will cancel each other. So, you have u 2 plus u 3 minus u 2. So, minus u 2 cancels out. So, you have u 3. So, u at x 3 is u 3. Similarly, here also if you put for the third element also, if you put x equal to x 3, then what happens? X 3 here becomes 0, this 0 becomes everything is 0, hence you have u 3. So, that really means again u this side for this element and u for this element both will have the same value, that is u 3 at this point, hence it is continuous. So, this scheme guarantees using nodal displacements in the test functions guarantees continuity. Continuity, which continuities? C naught continuity. So, at least this will be C naught. Yeah. So, automatically it will be continuous, and this is what we want, So, unless we have that, if you you cannot get du over dx, which is required for calculating the values. Yeah. So, in the weak formulation we have du over dx. So, unless this is C naught continuous, you can't compute this one, and hence C naught continuity is required. We have been studying the computer friendliness. So, the second aspect of computer friendliness, so continued. So, computer friendliness. So, we have, like, finally the weak formulation, if you see, we have something like this one, right. So, we have dw over dx Ea du over dx and so on, right. So, what we see here is integration. So, how integration, we have to integrate these things be in the computer itself, right. So, integration or numerical integration. Yeah. So, this is important, and this we will do probably in the next lecture video. Okay. So, that is why I am not discussing it, but this is a very important, and hence we have to learn it and we will do it. Otherwise, we will not be able to implement on computers, and hence we have to do numerical integration. Now, next thing is easiness or elegance, right? Easy, elegant. Okay. Now, here what we are going to do is again writing this term, right. So, you have, we can even further make easy. So, whatever we had earlier, the notation like alpha naught plus alpha 1 x, we find this u1, u2, u3, u4, if you use them it becomes much easier, but still you have to see here you have x1 x, we have to keep track of all those also, right. You have to write many equations at a time. We want to do little bit differently so that it's even much easier, so we don't have to care about what is x2 x1 and all those things. As long as we know the L, it should be sufficient. Why to actually look at like what is x2, what is x1 and so on, keeping track of all those things. So, basically what I mean to say is it possible that just information about just one element is sufficient to compute a few things, at least a few things. Yeah. So, what I mean to say is, if somebody tells me that there is one element, the first which has the two nodes, node 1 and 2. So, node 1 and 2. Okay. So, basically here we are talking about working in the local coordinate system. Rather than the global one. So, local or element coordinate system. What I mean to say is, why not do something like we did in direct method? We looked at one element, we computed the stiffness and all, and then we assemble them. Yeah. If we assemble them and do like that, then we have to just worry about the elements only. We find out what is the stiffness matrix for this one, and then we assemble in the global matrix. Yeah. So, why not do that? That is much easier, and that will be also like computer, we can implement on computer. Yeah. So, that will be the one thing. Secondly, it will be also elegant, it is easy to implement and everything easy to understand and all. So, basically here the idea is to use the element coordinate system rather than using the global coordinate system. Yeah. And then if we know how one element behaves, we can implement, we can actually compose the global matrix, and from there we will solve. So, basically can we do something which is close to what we have done during the direct stiffness method, direct stiffness method or direct method, as we did in the chapter 2. So, this actually we want, somehow we want that kind of system. So, that is much easier, and that will only possible when you have the local coordinate system or element coordinate system, meaning that our u also will be defined locally. So, basically u x local. Okay. So, that is the idea. So, how? So, basically we look at one element whose local node is 1, local node number 2, you have u1, this element number e. So, I will write element number e like this, okay, or maybe we write like this. This is node number 1, node number 2, and this is u1. Okay, so e1 we can write element number, since this is u2e. Yeah, so all this is local. So, and then we can define u now. So, instead of saying what we did earlier, like this one, ux equal to this and this, we will say something like this. We will say for node number 1, sorry, for element number 1, that is for, that really means x greater than x1 less than x2, that is what it means. So, element number 1 we had u e x equal to u 1 u, so here e equal to 1, e equal to 1 basically. So let us write this as 1, u 1 equal to u 1, here also it is 1, this is 1, this is node 1 plus u, right, u 2 1 minus u 1 1 divided by L 1 multiplied by, I will explain what is the meaning of that, multiplied by x, okay, x and x1, let us write x1 minus x1 1. Okay. What is the meaning of that? I am formulating everything in local coordinate system. So we find out the first element. The first element is basically this one from here to here, and everything I am writing in locally, meaning that our local coordinate system has something like this. So this is element number 1, element number 1, okay. This coordinate, also we can have x, instead of saying x1, this one is basically, you can call it this is local coordinate system, x goes like this, and this is the value, okay. So one thing here, this we assume, this we will assume to be 0, this one, okay, meaning that the coordinate system starts from 0, okay. So basically our for the element number 1, our coordinate system is like this one is x equal to 0 and this is x1 equal to L, okay. So we say x1, basically this is the coordinate system of node of element number 1, this is 1. So this is coordinate system of element number 1. So this is x1. So this is x1 equal to 0, this is x1 equal to L basically, right, okay. And in between, if you know the u, let us say u is given at this point, u is given to be u 1 1, meaning that this u is for element number 1 first node, and here this is given to be u 1 2, means displacement at node 2 of element 1. So this is node 1, this is node 2, all local basically, yeah, okay. So for this one, the u, right, for this one the value of u1, when you say u1 means displacement inside element number 1, okay, in local coordinate system. And we can write like this one, like this, yeah. So this will be simply since u x1 is 0 here, right. So this we will have 0. So basically it turns out to be simply u1x equal to u1 plus u2 minus u1 multiplied by x1 over L1, yeah, like this one. And same thing we can write for second element as well. So, if you compose the second element also, we will have coordinate system which will be x2, yeah. So, we had x1 here, now it will be x2 and then these points we have x21 which is equal to 0. Okay, so in local coordinate system the initial point will be 0. This point becomes x22 which is equal to L2. This is the length of the second element. So, this is how it is, and accordingly we can now write the, if the u, this one is u of at node 1 of the second element, this is u of node 2 of the second element. We can write displacement inside this element as u2, which is a function of u2 will be a function of x 2, yeah. Okay. So, this is not a square, this is to denote that these are related to element number 2. So, this is element number 2, yeah. Okay. So, we can accordingly interpolate. Now, u2x will be equal to u12, meaning that u of the second element at node 1 plus u2 minus u divided by L2 multiplied by x2, yeah. Okay. So, this 2 means node number 2. Okay. So, remember this is means the element number 2, this is the meaning of element number 2, yeah. So, this all element number 2, okay, and this means node 1, yeah, this means node 2 and so on. So, this is how we can write we can interpolate. So, this is we are interpolating, right. So, this is interpolation, we can write interpolation, and similarly we can write for third one, from here we can extend to third one. So, element number, if at all there is third one, yeah. So, our example, this has 3 elements, so 1, 2, 3. So, this one, for this example we can write the third one as well, element number 3, and we can write interpolation function u3x equal to u13 plus u32 minus u31 divided by L3, okay, multiplied by x3, okay. This means the x coordinate at any point basically for the third one. So, we are talking about third element which will have 0 to L3, yeah. So, for this, and x, this is x is going this way, x3 is going this way, Okay. So, basically we can write, if you had more than 3 elements also, we can generalize this as u of the element number e as a function of x e is given by u e1 plus u e2 minus u e1 divided by L e multiplied by x e. So, where e equal to element number. Yeah. So, in general we can extend it like this one, or we can write u e x e is equal to, we can write such a way that u e1 are together, and so that way what happens, we can write 1 minus x e over L e multiplied by u1 e plus x e over L e multiplied by u2 e. Yeah. Or simply we can write this as n e x, right, x e u 1 e plus n, write n 1, and then n e 2 x e u 2 e. Okay. Where n I e are called shape functions, or interpolation function. Okay. Okay, what is the advantage of doing this one? If you write this one, first of all it is elegant. We can write regardless of number of elements you have, you can write this way. Yeah, so for every element there will be 2 shape function n e1 and n e2. N e1 multiplies with u e1 and n e2 multiplies with u e2, right. Okay. What is the advantage of that is, this is piecewise polynomial, right. So, the u x will have now number of u e, depending on, like if you have 3 elements you will have u1, u2, u3, right. So, 3 of them. We can compose w also in this way. So, we can write w, we can similarly write w x as piecewise polynomial, means you can write w inside element number e as a function of the local coordinate system is equal to n e1, right, and then x e, and then w e1 plus n e 2 x e w e 2. Yeah. So, instead of writing u, you have written w, that is it. we can keep exactly the same expression. And what is the advantage of that? Advantage is, if you take the weak form, and what we got? We got 0 to L d w over dx E a du over dx equal to 0 to L bw dx. We can put these values, and here dw over dx, right. So, what happens? We can put accordingly. So, we have since u equal to summation of not u basically. So, yeah. So basically this is true for the whole domain. So, now since we have two kinds of things, I mean we will have piecewise polynomial, hence we have to write now write like this one, the 0, we can write this as 0 to L dw over dx E a du dx will be equal to, we will have summation of from 0 to L e. So, there are 3 elements inside this one. So, 0 to L domain has to be divided into 3 of them, right. So, we will have E equal to 1 to 3 because there are 3 elements, yeah, and then what we have? We will have d w element number over dx element number, okay, and then we will have E can be a function of x e, a will be function of x e we have to put, and then we have to put du over dx. So, we have d u e over dx e and dx e, right. So, since this is in a global coordinate system, we have divided this into, we are doing the same integration, but in local coordinate system. Anyway, in any case, this is the area under the curve, this is what the integration is, and as long as the area under the curve is correct, you can also write this one this way. So, what you are doing the same thing, you are now doing in terms of summation, because there are 3 elements, you are doing this integration by divided in 3 domain. Every domain will start from x e equal to 0 and ends at x equal to L e, length of that element, and you know that big L is equal to, so you know that big L is equal to summation of L e basically, right, e equal to 1 to 3 in this case, in this example, yeah. So, this is how you can write. Similarly, this also you can write the same way. So, we can write b 0 to L b w x as a function of x dx is equal to summation of e equal to 1 to 3. In this example, there are 3 elements, and then you have b 0 to L e, and b is a function of x e we have to write now, and also we have to write w e as a function of x e, right, and then dx e. So, the complete domain 0 to L we have divided into 3 of them, right. So, this will be L1, L2, L3, you add them together becomes L basically. So, this is how we can write. So, basically the whole equation now becomes like this: E equal to 1 2 3 0 to L, and okay. So, before doing that we can write okay, maybe we write them together, so no problem. So, yeah, D, this becomes L, and E, D W E D X E E X E A X E D U E over D X E D X E is equal to this, one, right, is equal to maybe we write like this, okay. Just we include here, automatically it means this equal to this. What is the motivation? Why did we do like this? Why do we want to write like this? This is because if we simplify this one, we will get some equation, something like this. We will get, this will tell that W1, sorry, so okay, before that I think let write one thing. We are assuming W one is equal to, let us call it capital W1, then W 1 2, which is meaning that W of element number 1 at node 2. For continuity, this has to be W 2 1, let us call it W 2, and similarly W 2 of element 2 equal to W 3 of at node 1 is equal to W 3, and similarly W 3 2 is equal to W let us call it W 4. Okay. So, this is because we had element and we have divided like this one. So, this point, this point, this point, this point. So, the first element of the first node of first element is W1. So, basically we are saying that this is W1, capital W1, capital W2, capital W3, capital W4, that is what we are saying it, yeah. And also the U will be U1 here, U2, U3 and U4. So, this is the global. So, these two are global, yeah, global, and this one we have the local one. So, these are the local ones. So, similarly we can also write the same as this, we can also write U11 equal to U1, U12 equal to U21 is equal to U2, U22 is equal to U31 equal to U3, and similarly U32 is equal to U4. Yeah. So that the for element we said what, this is the first element and the first node has U11 displacement, the second node has U12 displacement, but actually this local notation has to match with the global one, with regardless of whether it is a local, you are looking from the local point of view, means element point of view, or looking from the global point of view. In the both the things, displacement remains the same in the both the cases, hence the displacement has to match, and hence this is the thing that we have to apply, right. Okay. Now, if you have this notation, if you use it here, finally the why we are doing it, that simply this equal to this will make convert this into a matrix form. Okay. So, from the continuous system we are going to be a discrete system, we will get a matrix, and what we will get? We will get something like this, we will get W1, W2, W3, and we will get a big matrix here, and how it will be something like this, K11 of element 1, K12 element 1, K12 of element 1, K22 of element 1 plus K11 of element number 2, K12 of element number 2, K12 of element number 2, and we will have K, so all a small k. Yeah. So, either you can write 1 2 or we can write 2 1, it is the same thing, but you know that both values are same. So, plus here it will be K 2 2 of element number 2 plus K 1 1 of element number 3, K 1 2 of element number 3, K 1 2 element number 3, and K 2 2 of element number 3. So, we get this one. So, this will be 0 0 0, similarly it will be 0 here, and we will have 0 and 0 here. So, we have this, which is if you see, this one is 3 by 1, this is the 3 by 3, okay. And if you see, if you look at this one, this is a, you know, so we are integrating, so it has total has to be a scalar number, right. So, how will we get? So, here we have 3 by 1, here 3 by 3, so multiply it together, sorry, it is on 1 by 3, okay, just so this is not 3 by 1, but 1 by 3, 1 by 3, this is 3 by 3, so multiply 1 by 3 multiplied by 3 by 3 means it is 1 by 3 only. So, we get something to multiply with, which has to be 3 by 1, so that this will be a scalar. So, indeed there will be something here, something here, here basically, okay. So, let us call this one is u. So, let us write u here multiplied by u, yeah, where u equal to nothing but u1, u2, u3, u4. Okay, something okay. Yeah, okay, now I realize it is this is not 3 by 3, but 4 by 4, okay, and here also it should be 1 by 4 only, okay. So, we missed here W 4 as well, there has to be W4 as well here, okay, and hence it will has to be 4 by 1 by 4 matrix. So here you have 4 by 4, and this will we have to write transpose, right, so that u will be, so u is 4 by 1. Okay. So, so what you see, this one is equal to the whole thing whatever we have written here, this multiplied by this multiplied by this, where u equal to this one is equal to this. Yeah. So, this is that equal to that. Okay. So, I will also write like this one. Okay. So, that, okay, so let us keep it like this. I will write this whole thing is equal to 0 summation equal to 1 to 3 0 to LE d W E dx E E A du E dx E dx. Yeah. Okay. And similarly, similar thing we can get from the other one. Also we have 0 to L B also summation of E to 1 to 3 0 to L E B W E not W but X B X E times W E X E dx will be equal to something you will get like W1, W2, W3, W4, and you will get here F1, F2, F3, F4. Okay. Some constant it has to, because of this one this will appear, and because of all other things this will also appear. If you multiply them, this will what will make the whole thing you can describe like that. Now, you know that W is arbitrary, right. So, W x is arbitrary, hence W1, W2, W3, W4 are arbitrary except where u is defined, are arbitrary except where u x is known. Okay. Hence, what we will see is basically the whole thing cannot be 0, right. So, maybe one of them will be 0 because u1 equal to 0, hence w1 is 0, but this cannot be 0. So, that really means that it is only possible if this whole thing is equal to this whole thing. It's only tells you that this is k times u equal to f. Okay. So, the only thing that tells you that ku equal to f, where k is given by the one I wrote earlier. So, K1 1 1, K1 K1 2, K1 2 1, K 2 2 1 plus K 1, K2 1 1, and so on, right. 4 by 4 matrix that you see here, this the whole thing. This we are saying K, this is U, so U is this one. So, U is equal to U1, U2, U3, U4, and W is W is not there, and F is equal to F1, F2, F3, F4. Okay. Yeah. So, this is the advantage that if you write in this format, right, we get matrix system, the same thing that we got in chapter 2, this kind of thing we will get, and hence we do like that. More details we will have later on, but you automatically you know that U1, U2, U3 are the either we are given or we have to find out. If you have to determine how you find out, right, and this we have to integrate. The only thing is now remains that how to find out this one. This also you can write K E I J is equal to 0 to L E, and then it will be D U E over d x E, right. So, here actually if you look at, okay, maybe since d u E over d x E term is there, and you know that d u E itself has two things, is equal to d x E, and it will have n 1 n E 1 x E times u thing is there, right, u 1 of 1, sorry, this will be E of 1 plus n 2 E x E times u E2 is there, right. So, like this one. Hence, what you see here, you will get derivative of this, right. So, this is becomes a constant now, because this is the nodal displacement. So, this is going to apply to this only, because this is only the function of x, and this also, right. Hence, you will see that in K derivative of n will appear. So, we can write like this one, K E I J equal to 0 to L E, then d n I E over d x E times E x E, okay, times A x E times d n j E d x E, okay, times d x E. So, this is the how K I J we can find out. These all are coming from the same equation, that the weak formulation, only thing we are adding the u is not it is not the same, we are not using a single polynomial, but 3 polynomial, and if you put those values automatically you will get K I J, right. So, this if you want to find out k111, what you have to do, you will put here e equal to 1, I equal to 1, j equal to 1, and you do it, you will get it. Now, how to find out f? So, you can put this value, like in order to find out f, this will be, you can find from here using this equation, right. So, here what do you have? You have W e term here and B, this is a W e. W e itself, you know that it will have n term, right. So, see here, yeah, W also has n1, n2 term. So, what we will get is basically f, you can write like this one, f1, f2 and like this one. So, f1 is nothing but f1 is equal to f due to first element at node 1, okay. f2 will be equal to f due to first element at node 2 plus f due to second element at node 1 of that element. Similarly, f3 will be equal to f second element second node plus third element first node, and f4 is equal to f of third element at second node, where f e I is equal to 0 to L e n, right, n e I x e, then b x e d x e. So, this is the formula, right. This is the how this you can calculate, and once you know this, you can calculate f1, f2, f3, f4. Once you know f1, f2, f3, f4, you can compose this f vector u1, u2, u3, u4. You have to find out if u1, which may be displacement at x equal to 0, which is x displacement at x equal to 0, and that you can maybe 0, you can put 0 here. K you will find out the way is written here, right. And we will do the we solve the problems and all, well, like but this gives you the idea what is the motivation behind using the local coordinate system, how it becomes, what is the idea about the piecewise polynomial, so that simply we get ku equal to f, and this is why we have been doing all this, okay.